if you use Google Maps and you zoom out, you get to a 3D map showing like the Earth, and you can rotate it as a globe. And so the idea is that these mountains that exist in the eastern United States, I mentioned this very briefly. So the eastern United States, the Appalachian Mountains, run from like Georgia up through like New Hampshire, Vermont, Maine, and then that mountain chain continues up along and into the eastern provinces of Canada, and then that range continues up along and in through Scotland, and up into the Nordic countries. So really, the types of rocks and the types of features we find up in Norway and Sweden and then down through Scotland are very similar to those we find in the eastern part of the United States. That's a pretty good piece of evidence too. And then, let's see. So that's in that set of slides. So this is another way that that illustration is seen. So in that most recent Pangean continent, the way that these mountains form is as Africa and Europe run into North America, there's like a collection of these continents, and that builds the mountain up. So if there's motion of Africa and North America together, that causes the folding of the mountains. Similarly, North America, Greenland, and Europe is supposed to form this mountain. So this mountain chain actually form, but then whenever they separate, and it forms the Atlantic Ocean, that same mountain chain, the Appalachian Mountains and the British Isles and the Caledonian Mountains, those mountains still exist and have similar features, similar shape, running in the same direction. That's a pretty good piece of evidence. I also mentioned the thing about the fact that the top of Mount Everest is ocean floor as a result of India running into Asia. And there's lots and lots of websites describing the different layers of rock. Here you can actually even see like visible lines that run horizontally along the top of Mount Everest, the different layers of seafloor sediment. And that seafloor sediment contains all kinds of different fossils from seafloor. It's a good indication that there's motion of the continents relative to each other. Another fact is the idea of similar glacial deposits on lots of continents. So glaciers can extend from the polar regions toward the equator, but only in places on the Earth where it's very cold due to glaciation. And as the glaciers move, they drag rock across the land and leave glacial striations on the surface of rock. And so there had been in the past glaciers both in the northern hemisphere and the southern hemisphere, but the best evidence of the motion of the continents relative to glaciation is in the southern hemisphere. So like, if you have this big continent of Pangaea, where there's South America and Africa and India that are much further south than they currently are, and a glacier spreads from the South Pole toward the equator, it leaves these lines, these glacial striations on the rock as the glacier moves across the land. And the direction of the movement of the glaciers should be from the south toward the equator. And so not only for the southern tip of Africa do you find the idea that there are these glaciers which could never form today in the southern tip of Africa, but that Africa was kind of twisted or rotated kind of like clockwise relative to the way it is now. As you fit those continents back together and put them into places where the glaciation could take place, you find that there's consistency in the direction of the lines. There aren't too many puzzles about this. And then as the continents move apart, you find those same glacial deposits called glacial till, which is like small gravel that settles out into the ground. And the stripes or striations, the drag marks that were in that video on the surfaces of rocks. And those same glacial deposits with the similar types of gravel and the similar types of striping exist in rocks in South America, Africa, India, and Australia, when these four places were all together up against Antarctica. So that's another important piece of evidence. And then the last piece of evidence is comparable fossils on different continents. So they mentioned in that video we watched specific fossil species that are found in common places or in different places on the Earth, but in places that were seemingly once together. So similar fossils that exist in southwestern Africa and eastern South America, when these two parts of the world were together, it's reasonable that the land animals could move, across the land. And then once the ocean starts to form, those become isolated species. And we notice that after the point when they move apart, those isolated species then sometimes evolve a little bit differently and a little bit separately, like on their own. So that's just kind of a review of the basics of Alfred Wegener's hypothesis about how continental drift could have taken place and how the formation of the oceans go. So there's some space you can, write some thoughts about each of those four ideas. So those four ideas are the big hypotheses for the way we currently understand continental drift. The term continental drift is oftentimes now called plate tectonics, which means a slightly different thing, but is very similar in its concept. And what you need to get a good understanding for is how that drift even takes place. So in the folder for chapter 2, there's another section that's about, let me change to a different screen here. Share. There's another file that says geomagnetism. So it turns out that the Earth itself is one giant magnet. And one way that we understand how this motion ever took place is by understanding the Earth's magnetic field. So, a lot of topics in oceanography can be very multidisciplinary. Like, we're not just talking about the water and the ocean, but how we understand how these things all come to be true is by making big comparisons between different things. Okay, take a look at the left-hand globe, like this one here. Do you notice anything weird or wrong or kind of different about the labels that are on the left-hand globe? Let me zoom in a little bit. That's on this one. What seems weird or strange or wrong about the labels on the left globe? Yeah, AJ. Yeah. Okay, so this is North America, South America. So we're right here. And this has S up there and down there. We usually call that direction north and that direction south. True, right? And it's labeled North Geographic Pole, but then South Magnetic Pole. And similarly, down here, so South Magnetic Pole, North, or South Geographic Pole, North Magnetic Pole. I don't know why that. Click to join audio. I don't really want to join audio. So here's the thing about the Earth itself. We have a North Pole and we have a South Pole. The pole itself on this globe is like that place where you fill the air up, and on the bottom it's this little circle down here. And the idea is that the Earth rotates on its axis, the Earth spins on its axis. And that axis on which the Earth spins defines the North and South geographic pole. In other words, if you draw a line through the center of the Earth, or if you put a rod through the middle of the Earth rotates about that point. And because the Earth rotates relative to the sun, that's how we get day and night. So when it's nighttime, like when it's, here's North America, if the sun's at the back of the room, the sun shines on us and that's daytime. As the Earth rotates, so that North America is now on that side, then it's nighttime. So the rotation of the Earth gives us relative daytime and nighttime. And that rotation takes place through an axis. That axis defines the north and south geographic pole. One way to navigate on Earth is with a compass. That compass can tell you what direction is north and south. But the compass aligns with the Earth's magnetic field. And the Earth's magnetic field is not exactly in the same direction as the direction in which the Earth spins or rotates on its axis. So what I'm saying there is that there's a place that is the north pole of the Earth in terms of its magnetic field, and it's not exactly the same place as the place where the Earth rotates on its axis. This illustration, see that red, like that red line? That is the North Pole, the place around which the Earth rotates. Down here, this red line is the place around which the Earth rotates the South Pole. But the place where the magnetic field lines come together, the place that's magnetic north, is a little bit away from the geographic North Pole. So a compass does not actually point directly to the place where the Earth rotates about its axis, but points to the place where the North Magnetic Pole is located. So now here's the next thing. I keep saying north is up at the top. If you have magnets, what's true about the way in which magnets attract each other? Like, what kind of magnets attract each other? What has to be true? Yeah, they have to be opposite. Okay, so if you have a north pole of a magnet, it attracts the south pole of another magnet, and vice versa. So here's the way in which we talk about magnetic poles with compasses. If you have a compass, like this is an illustration of a compass. Compass is a device, usually with liquid inside it, and then there's a magnet, and one pole of that compass will be called the North Pole. So on a compass, this red needle is the North Pole, and the white needle is the South Pole. So if you call this pole of the compass the North Pole, and the white end of the compass the South Pole, the pole of the compass will line up with the opposite pole of the Earth. Meaning, when you call this pole of the compass north, it's going to align with the south magnetic field of the Earth. So if the Earth is a big magnet, this North Pole is down south, and the South Pole is up north. The illustration is not backward. Instead, when you define the North Pole of the compass, it's going to line up with the South Pole of the Earth. And the South Pole of the compass is going to line up with the North Pole here in terms of the magnetic field. All right, so you might say, well, what does this have to do? Anything at all to do with oceanography at all? And it has a lot to do with oceanography for a couple different reasons. First off, that core of the Earth and the magma in the center of the Earth is mostly molten iron and nickel, and it's in motion. And that motion of the molten iron and nickel is what generates the magnetic field for the Earth. That the molten rock in the middle of the Earth is moving is what drives continental drift anyway. As this fluid, the middle of the Earth is a molten hot fluid. As that fluid moves from the core to the crust and then back to the core, it ends up setting up currents, which go in like a circle. And as that motion of that magma gets to the surface of the Earth and moves along the surface of the Earth underneath the crust of the Earth, it drags the crust along. So that the iron in the Earth is moving, generates a magnetic field, and it also causes the plates to move in the first place. If it were that the core of the Earth and the magma in the middle of the Earth was not in motion, the Earth would have a different or non-existent magnetic field, and continental drift would slow down and not take place. But there's another thing that the magnetic field does. It's very important. This will be an important topic as we go through things. Is that sometimes that magma comes through the crust and lands on the surface of the Earth in a volcano. And as that magma comes up through a volcano and cools on the surface of the Earth, because lava contains a lot of iron, when that lava cools, it locks into itself the direction of the Earth's magnetic field. What I'm saying there is, if lava comes through the Earth in a volcano and cools on the surface, that rock, whenever it cools, will be magnetic. and the direction of the magnetic field on the surface of the Earth will be in exactly the same alignment as the direction of the Earth's magnetic field at that moment in time. So, if at some time in the past you get a continent where there was volcanoes and the lava cools on the surface, it tells you the direction of the Earth's magnetic field at that point in time. And then if that plate on the Earth rotates or moves to some new location, you can relate the direction of the magnetic field in the past to the direction of the magnetic field now. So magnetism is going to play a very important role in understanding things about the ocean floor. One way we know about the Atlantic Ocean's motion, or the Atlantic Ocean getting wider as time goes on, is that the Earth's magnetic field changes direction and changes strength over time. And as new seafloor is formed with volcanoes on the ocean floor, the direction of the magnetic field at the time when the lava forms creates what we call stripes on the ocean floor. In other words, like if the Earth's magnetic field changes direction or changes strength over time, the direction of the magnetic field in the rocks on the ocean floor change the direction that the magnetic field is locked in them as time goes on. So here's a thing that you may or may not know. It's a very important current event in what's happening with the planet itself. This map on the left shows the idea that the Earth rotates on its axis, and that's this blue line that says NG and SG, North Geographic and South Geographic Pole. But the direction of the Earth's magnetic field is off at an angle just a little bit. And that's because the North Magnetic Pole and the North Geographic Pole are in slightly different locations. On the right-hand map, this is a map showing northern Canada. So there's a territory called Nunavut, which is a northern province of Canada. And the first time the Earth's magnetic field location was determined based upon careful measurements of the Earth's magnetic field at the time is in 1590. So on this map, it shows 1590. And then this is the actual rotation point of the Earth. This is the geographic North Pole. So it turns out that the North Magnetic Pole has moved over time. These are years. So the Earth's magnetic pole moved toward the north, like 1632. And then it moved like down to the south, 1700, 1730. And then it kind of like moved south again through the 1800s. And this mark, 1831, is the first time that an expedition reached the position of the Earth's magnetic North Pole. In other words, you actually go to the place. That's the place, that's the North Pole of the Earth, 1831. Now, if you look at the dates on here, from 1831 to 1904, that's about 70 years. The Earth's magnetic North Pole only moved a very short distance. This is like 73 years short distance. And then from 1904 to 1948, in the next 44 years, which is less time, the direction of the magnetic field and the distance change is huge. And then you get to the 1960s, 1970s, 1980s, 1994. So from 94 to 2001, in only just 7 years, the position of the Earth's magnetic North Pole moved this enormous distance. So it only went like this far in 70 years between those two yellow orange dots, but in just 7 years went that far. And it turns out that the Earth's magnetic field is changing its position faster now than it ever has in the past. There's 2001, 2010, 2020. This is actually the North Pole and the international date line. So it turns out that the magnetic North Pole has moved toward the North Pole consistently. And then late last year, the North Pole is actually heading south. That's going around the other side of the Earth. What we don't know and what we can't tell is, will this speed continue, which is an extraordinary speed. So just in the last 20 years, which in terms of geologic time is a tiny snapshot, This distance from here to here is over 100 miles, just like 20 years. So what if, it's another 1,000 years from now? Will the magnetic North Pole slow down in its motion, head back toward the North Pole, geographic North Pole itself, or will it continue south? We know that in the Earth's past, the poles have been in completely different directions. In other words, the magnetic field of the Earth has switched from being like north is north, south is south, to being in the total opposite direction. We know that because when we study the rocks on the ocean floor, as the ocean spreads and as new lava forms on the ocean floor, when we study those rocks, the direction of the magnetic field changes. And oftentimes the period of time when the field switches direction is really short, it's very quick. Really from 1590 until like 1990, in these 400 years from 1590 to 1990, the magnetic field just kind of like wavered around a little bit. So in 400 years, it stayed in this little region. But then in just the last 20 years, has moved dramatically, moved really far and really fast. So what does that mean for the future? Well, maybe like 50 years from now, it's not impossible. The Earth's magnetic field may be in the totally different direction. So that if you have a compass, which normally points north, like heading toward Canada, that north may now point south, like toward Mexico. We can't know, and we can't say for certain what the future brings, but one thing we do as scientists is say, well, if every 5 years it moves about the same distance, and if that speed and direction is consistent, you just extrapolate and say, well, if it was here in 2000, 2005, 10, 15, 20, where would it be in 2025? Well, my guess is it would be like up here, except it may slow down, it may change direction. The past shows us that it's very difficult to predict the change in the Earth's magnetic field. So we could be going into a time of field reversal. We just don't know. But what we do know is that whenever there are recent volcanic activity where new lava is formed and falls on the Earth, we can be more certain that we know for sure that the direction of the Earth's magnetic field is closely related to the direction of the magnetic field that's in the rocks when it gets laid down when the volcanoes actually put the lava out. So you're actually living in a really exciting time in terms of the Earth's magnetic field because 34 years ago, it wasn't so certain that the magnetic field was changing direction entirely, but we have a much better understanding now that the Earth's magnetic field is moving along much more quickly than it ever was in the past. The Earth's magnetic field plays a very important role for us on Earth. It plays an important role with navigation for animals we'll study. Sea turtles, lots of birds, they navigate with the Earth's magnetic field. They're able to sense the Earth's magnetic field. You can't sense it, but lots of animals in the ocean and on land and in the sky can sense the Earth's magnetic field. So there are questions in oceanography like, if the Earth's magnetic field changes direction and magnitude very rapidly, does that change the ability for animals to be able to migrate over long distances? If when you're born as a sea turtle, and then 60 years later, if the magnetic field is significantly different, have you been able to adapt to the change in the magnetic field? Or has that caused changes in migratory patterns for the animals themselves? So this is an exciting time to be able to study those kind of things, to see how those changes take place. So here's what that means for us, like in Williamsport. This is a good thing to know if you're like an outdoors person or a hunter and you use a compass to navigate, although people use GPS very heavily now. There are places on the Earth where the direction of a compass pointing toward the North Pole is the same direction as the North Pole itself. This is a map called a declination map. And anyone who lives like along this green line here, like here in North America, South America, or throughout Europe and Africa and Asia, all the people who live on like the zero, a compass pointing north, that's the direction of the North Pole, exactly. But anybody that's to the right of the green line, like here in Pennsylvania, the Earth's magnetic field, the magnetic North Pole, is like to the left of the geographic North Pole. In other words, on this flat map, it's like this place is the geographic North Pole, but the magnetic North Pole, well, in this map, it would be like in line with the green line, MN. Yeah. But if you're to the right, the deal is that the direction to the magnetic North Pole is slightly to the left of the direction of the geographic North Pole. And there's an angle that exists between those points. But this is illustrated on a flat map. It's a little more complicated on a globe. So what that means here in Williamsport is that if you take a compass and you want to use that compass to point to the North Pole on this map, we define north, the direction to the North Pole, to be exactly straight, like perpendicular to a latitude line. A compass instead will point to the left of that direction by 11.5 degrees, which is a really big difference. That's a substantial difference. So what I'm saying there is, like, when you take a compass with a magnet, you're trying to walk in the direction of north. That's not north. It's actually off by 11 degrees, which over long distances is pretty substantial. So the big story is that the Earth has a magnetic field. The magnetic field of the Earth changes in direction over time. It changes its position over time, changes its strength over time. That plays a role in navigation for both us as people with our equipment that we use. Like you have a compass built in. Most cell phones have a compass built in, and that uses a magnetic field sensor. And that compass's datum is updated on a regular basis to accommodate changes in the Earth's magnetic field. You don't know that it's updated, but it is. But that we know that the Earth's magnetic field changes direction and position over time helps us understand how whenever we study the rocks on the Earth, we can understand that at different times in the past, different places on the Earth were in different positions, and that those positions move and change. So it's like, when we say oceanography is an interdisciplinary field, I mean, right away we've talked about biological concepts. We've talked about things about, geology. We got things about like magnetic fields. Things get pretty complicated pretty quick. Okay. I don't know how much time we have left. All right. Let me show you, we'll just show you this one. Let me do it on this other computer. I can put it in the chat too. So if you're remote, this video is a good one to watch. Think about the movement of the magnetic field. Add this to the chat. It has a pretty good illustration. So if you're remote, best thing to do, you can watch this video, and that's all you kind of really need to do for the period today. We'll watch that on this one. Courses. That one logged me out. Close. I know what I can do. I've got it on the chat on this one. Oh, I lost my other window. What a pain.
It's like the easiest decision in the history of.
Hate when it's a 15-second ad.
You may have heard that Earth's magnetic poles tend to move around. I mean, so do the geographic poles, but magnetic north and south are really mobile. And magnetic north in particular is
What's that?
moving real fast, like
Yeah.
way faster than we thought it would. And the scientific community is coming up with some really exciting and creative ways to figure out why. The prevailing theory about why our planet has a magnetic field in the first place is because of what's under the crust. Dynamo Theory, as it's called, is the idea that the molten metals of the outer core, like iron, are being convected, basically swirled all around the Earth's interior, around that solid inner core. This continuously creates electric currents as charged particles move through this liquid metal. And in combination with the rotation of the Earth, it becomes what's called a dynamo, the source of the magnetic field. This also explains why magnetic poles are not necessarily fixed points, because the liquid that creates that magnetic field is turbulent and always shifting, and the poles move as the fluid does. Right now, for instance, the North Magnetic Pole has been slipping down into Siberia for the past 150 years or so, and it's speeding up. Our magnetic field actually has a name. It's called the magnetosphere, and it plays a crucial role in making Earth a habitable planet. It wards off much of space's harmful radiation, like cosmic rays, acting like an essential protective cloak around the Earth, which is one reason why scientists and governments are so invested in knowing how it works and how it will behave, like the World Magnetic Model, for example. This huge and innovative computer model of Earth's magnetic field behavior is used by many international bodies as the guiding standard on what the world's magnetic field is up to. It combines sensor measurements of the field's strength and position, measurements which are then used in simulations of the geodynamo's past, present, and future behavior. The WMM releases updates to the model every 5 years, but in 2019, it was forced to release a mid-cycle update because magnetic north has been sauntering vaguely downwards much faster than anticipated. The perfect example of the fact that even though we're measuring and predicting to the best of our abilities, the geodynamo is too unpredictable and complex to make a truly complete model of it. That uncertainty means scientists are also looking for experimental ways to further probe the Earth's magnetic behavior, which typically involves creating models of the Earth out of liquid sodium, which is quite the commitment because sodium is a highly reactive metal that is extremely difficult to handle and likes to spontaneously burst into flame. New sodium ball experiments are being used in several labs worldwide, and in combination with improvements in computing and machine learning, could help us gain more insight into how Earth's magnetic field will change and how we can prepare for it when it does. Because what does a shifting magnetic field actually mean for us? What poles would mean the names of Earth's hemispheres may be a bit confused for a while, and compasses would point in the opposite direction than they did previously. But more importantly, as the poles shift around, the magnetosphere could get weaker, with several smaller magnetic poles popping up in other places around Earth. A weakened magnetosphere means many things. The northern lights will be visible in new parts of the world, for a start, and all our satellites would need to be extra fortified against radiation, or we risk them getting totally fried by space weather like solar wind. Electronics here on Earth would be extremely vulnerable to interference and destruction by space radiation too, like our power grids. And that's not even mentioning the human health effects of being exposed to much higher degrees of radiation from space, which I tell you are not great. We know from studying magnetic inclusions that Earth's magnetic field has flipped entirely in the past. They trade places about every 300,000 years or so, but it's been over double that amount of time since the last time we know they flipped. So we are long overdue for some magnetic migration, and it's happening fast. And scientists are working hard to understand why and how they move and what exactly it may mean for us. And they do. The next update for WMM is expected in early 2020. Do you want to?
So, it turns out that like as we learn more about the Earth, we find out that things happen at regular periods in the past. Sometimes, our understanding is that about every 300,000 years or so, the Earth's magnetic field switches direction, and it's been about 600,000 years. So it's like you could say we're overdue, except it isn't necessarily exactly periodical like that. But I don't know. It is what it is. There's nothing you can do about it. I mean, you just got to go for it, right? It's kind of like the Earth gets hit by big asteroids once in a while, right? And, you take out the dinosaurs, you hurt stuff. Nothing you can do about that either. I mean, the best you can do is try to understand what happened in the past, try to develop models to predict the future, as time goes on, see how well it fits, and then, you know, try to be prepared in some kind of way, right? Changes in the Earth magnetic field, like how would it affect life for humans? It's not exactly clear, but you know, we've had a good run on this Earth, right? Like there hasn't been, I haven't had, you know, cataclysmic, you know, meteor impactor. It could be that the incredible development of intelligent life, like with humans and other things, is as a result of a stable magnetic field for a very long period of time. You know, if a weakened magnetic field causes more solar radiation to cause damaging effects on the surface of the Earth, it could affect, you know, animals in a negative way, right? So, not to say we're just kind of fortunate, but that could be part of the reason why, you know, things have been good for a long time, right? This is not like it's scary or something. It's just like it's a reality. It's a reality. It's amazing. It's really cool. You know, when I first learned about magnetic declination and first magnetic drift, it was in the 1980s. We're still kind of drifting around, but it's like every year we're like, oh, is it going to slow down more? And the story just continues to be, no, it's still going, and it's going faster than it was before. And the mid-year update in 2019 was pretty shocking. Like aircraft that have to navigate, they have compasses on board and GPS systems. Those begin to fall out of alignment. In other words, the plane thinks of those waves going by GPS, by satellite, thinks of those waves going by magnetic field. And when those fall out of alignment, aircraft have difficult time navigating. Same thing with Navy ships. So the mid-year or the mid-cycle update 2019 helped correct those kind of problems. Those updates are automatically pushed out to your cell phone too. You don't realize it, it's pushed out. So GPS systems in cars, like and like some cars now have like a compass built in. You know, just it generically tells you like north or northeast. That's not going to change very much. But modern cars have, you know, updatable systems that come down by satellite, and those systems can also be updated, you know, for directional things. You know, you think 20 years sounds like a long time. That's not time. Geologic time in the history of the Earth, 20 years is nothing. It's incredibly rapid, you know, incredibly fast paced. All right, we'll do much more with magnetic field rocks and stuff like that. This weekend, one of the aquariums is going to be removed from the hallway, and the one that's closest where it has all that salt on it, that's going to get fixed this weekend. Table windows on. So coming on Monday, the aquarium on. It's been leaking for a month now. It's not disappeared. Our oldest aquarium, one from it's the smallest of the four. It's been there since 2007. Yeah, I have to take the glass out of the hallway. You know what I mean? So, yep. No, not take the aquarium apart, but you know the glass in the hallway with the tableware. I have to take that out. And I meant to actually do it last spring. But, you know, yeah, so 2 of the 4, I'm gonna fix them. We're actually taking the windows out today.
Yeah,
And this weekend I'm gonna fix it.
over there, like the little one.
Yeah. That's a whole other thing. I'm gonna get that all fixed up.
See ya.
See ya.